Section 2.3, page 3, the last page for this section. Example 2 asks us to find the equation of the tangent line for the curve y equals x square root of x, specifically at the point x equals 4. So the goal is we're trying to find the equation specifically of the tangent line. But whenever we need to find an equation, unless you know the y equals mx plus b trick, we tend to use y minus y1 equals the slope m times x minus x1. So we'll be filling in x1, y1, and the slope. So first, let's go ahead and use the fact that we were given that x equals 4, and therefore that's what we're going to use for x1. Next, we want to find y1. And so that's really just the output of the function, and this is where both the curve and the tangent line cross each other. So we're going to plug the x equals 4 into the function of x square root of x. So put a 4 where x is, put a 4 where x is. The square root of 4 is just 2, and so I have 4 times 2, which is 8. I have my y1 figure. The last thing I need is to find m. Now remember, by definition, m is the slope of the tangent line. That's what we're trying to make, is a tangent line. But the way that we get the slope of the tangent line is the derivative. So I'm going to go back to my function of x square root of x. First, I'm going to rewrite the radical portion to be to the 1/2 power. I'm thinking of this first x having an invisible, which I've now made visible, 1 exponent. And because I'm multiplying the same base, I can go ahead and add those exponents, where 1 needs to be thought of as denominator over denominator. So I have a same denominator of 2, and I can add the 2 plus 1 to get a 3. Remember, I haven't taken a derivative. All I've done is rewritten the question. Now I can take a derivative, so I'm writing y prime, which is my m. I'm moving my exponent out front, and I'm subtracting 1 in the form of denominator over denominator. 3 minus 2 is 1 over that same denominator. Now remember though, this is just y prime, the generic slope of all the tangent lines to our function, but I don't want any slope of a tangent line. I specifically want this when x equals 4. So I'm going to take this generic derivative formula and I'm going to plug a 4 in for x, which basically means I'm taking the square root of 4, which is 2, and that 2 gets multiplied with the 3/2. So I could have written this as 6/2, but in the end, I could have also canceled the 2's. I need to simplify it down to a 3. So I've got y minus y1, where we found that y1 equals 8. I've got equals the slope m, and we found that m is 3. And times x minus x1, where x1 was given to us in the question as 4. So I just need to clean this equation up. So I'll start by distributing the 3 to the x to get 3x, the 3 to the 4 to get a 12, but it was minus, so I've got my minus 12. And then I'm going to move the 8 over by adding the opposite to both sides. Negative 12 plus 8 is negative 4, and I have my equation of the tangent line. This is the answer. The next thing is to talk about higher order derivatives. We've already talked about that the derivative of a function, where a function can be thought of as telling you a position, its derivative is velocity, how that position is changing. Its second derivative is acceleration, telling us how velocity changes. And this pattern continues where you can take a third derivative, an nth or generic derivative. So noticing closely the directions for example 3 ask us to find the second derivative of some given function. So The derivative of x to the fifth is bring the 5 out front, subtract 1 from the exponent, and I have 5x to the fourth. My minus 7x squared will bring the 2 out front to multiply with the negative 7 to give me negative 14. And when I subtract 1 from a 2, I get a 1, but we're not going to write the 1. The derivative of just x is 1. We've talked about how the derivative of x alone is 1. 23 is really a constant, and the derivative of a constant is 0. And the derivative of the cosine is the sine, but we wrote the word sine, so we put the negative. So cleaning all of this up, we have 5x to the fourth minus 14x minus sine x. And that was our first derivative. But now I'm treating the purple function as a question. The derivative of 5x to the fourth is to multiply 5 with the 4. Subtract 1 from the exponent to get 20x cubed. Negative 14x becomes negative 14 times the derivative of x, which is 1. And so we just have minus 14. And the derivative of negative the sine is negative the cosine. Now be careful. The derivative of sine is just cosine, but we were subtracting the last term, so we're subtracting that derivative. It's not that the derivative itself was negative. And I recognize many of you probably could have solved this problem without even writing anything, but in an effort to demonstrate where your knowledge comes from, it's important to write that first derivative before you write your answer. The last thing to discuss is the fact that the sine and the cosine, they have a pattern when it comes to derivatives. There's a lot written here, but let's just go ahead and focus over here on this left side. I'm given the cosine of x. When I take the derivative, I'm going to write the sine, and because I wrote sine, I put a sign. I've got the negative. When I take the second derivative, we just saw this. The derivative of the sine is cosine, but I have a negative that comes down. If I now take a derivative, the third derivative of my question, I leave this negative here. I take the derivative of the cosine, which is negative the sine, and because I have a negative times a negative, I'm just going to have positive sine x. And finally, you only need to take the fourth derivative to notice a pattern, that the derivative of the sine is the cosine, but hopefully you picked up that was the question. These two match. So since we're repeating the question, then at most we can think of 4 derivatives that occur where actually it's 3 different derivatives and the fourth derivative is a repeat of the question. So we're going to consider dividing by 4. So if I was to ask to take the cosine of x and find the 19th derivative, I'm not going to write 19 derivatives out. I'm going to divide by 4. And 4 will go into 19 4 times, which is 4 times 4 is 16, and it subtracts with a remainder of 3. So I just need to find the third derivative. Let's go back and tie that in with what I've written off to the right. 4 divided by 4 has no remainder, so it is the question, which is my fourth derivative. If I divide 4 into 5, I'm going to get 1 remainder 1. So this would have been the next derivative, the fifth derivative. So each time I'm dividing by 4, I'm really saying, okay, we've got these 4, and how many after that? We've got a bunch of these sets of 4 are happening. And whatever that remainder is, that is the derivative you have to take. So you'll never be taking more than 3 derivative deep. So when I said the 19th derivative is the same thing as the remainder 3, the remainder 3 is to find that third derivative, which is positive the sine of x. I also have the 19th derivative. So like over here, it asks for the 81st derivative. So I'm going to divide by 4 because there's only a pattern of 4 derivatives I need to worry about. 4 will go into 80 20 times. 81, sorry, 4 times 80 is 4 times 20 is 80 with a remainder of 1. So I just need to find the one derivative, the first derivative. Well, the first derivative, we're still doing cosine, is negative the sine of x. So without taking a derivative 81 times, I've got the 81st derivative of cosine of x. And the same thing happens with sine over here. We have our question. We take the first derivative, which is cosine. The second derivative is negative the sine. The third derivative is to leave that negative sign, and the derivative of sine is cosine. And then when I get to the fourth, it should equal the question, but remember, I've got this negative sign that I'm leaving, and the derivative of the cosine is negative the sine, but a negative times a negative is positive. The fourth derivative did repeat the question. So instead of being asked the 81st derivative of the cosine, I could be asked the 81st derivative of the sine.